Good morning. All right, we're going to look at something called trigonometric integrals today, and this is section 7.2 from Stewart's Calculus. All right, and so here's the idea. I'm going to give you an example. Well, let's look at a couple examples, see if we can develop a strategy, and then from there, let's formalize it, um, to be a little bit stricter, okay, or a little bit more formal. So here's my first example. I want to integrate cosine cubed x dx. Okay, cosine cubed x dx. Now, I look at this and first I want to try to do a U substitution maybe, but I mean, what could you do? If you let U, let's let U be cosine x, then du is the derivative of cosine, which is negative sine x dx, and that is not going to work for us at all, right? I mean, I don't have any signs in it, okay? So this is going to require a trick, and a few things we need to keep in mind today. We're going to need to know some trig identities. All right, and the first one, and the one that we're going to use most commonly, is we have to remember the Pythagorean identity, that cosine squared plus sine squared equals 1. And we need to be able to manipulate that algebraically. So 1 minus sine squared is cosine squared, or 1 minus cosine squared is sine squared. We're going to use both of those facts, okay? Another one, right, is that 1 plus tangent squared equals secant squared. We'll need to use that one. That's also a Pythagorean identity. And we can manipulate this one as well to solve for tangent, to say tangent squared is the same thing as secant squared minus 1. Okay, so we're going to need to know those. We'll also need to probably use the half angle identities, and we'll actually have to use the sum to product identities as well, or product to sum identities, which are the identities that when I teach trigonometry, I tell them, you'll never see this, okay? And we don't use it very much. All right, so anyway, how do we integrate cosine cubed? And I've kind of tipped my hat a little bit because I say, hey, we're going to need to use some identities here. I think we're going to have to use some identities here. All right, so we're integrating cosine cubed dx, and here's the trick. Here's what we do. Let's take out one cosine out of this. So I'm going to factor this a little bit to get cosine squared times cosine x dx. All right. Now, why does this work? Because now notice that I can use a trig identity on the cosine squared. So if I can get an even power of cosine by itself, maybe I can simplify that through some trig identities. So what I'm going to do here then is I'm going to rewrite this. Instead of cosine squared, I'm going to write it as 1 minus sine squared. And then I have the cosine x dx. And in a surprising move, my u for the U substitution is going to be sine x. So then my du would have to be the derivative of sine x, which is cosine x dx. And now look, once I do that, I have the integral of 1 minus u squared du, right? There's my du, there's my u squared. I have the integral of 1 minus u squared du, which is just a polynomial. So actually this is one of the easiest integrals we could have come up with. And to integrate that, let's see, we get the integral of 1, which is u, and then what, 1/3 u cubed plus c, just using antiderivatives. And now I can plug it back in using my U substitution, and I have, what was u? Sine. So I have sine x minus 1/3 sine cubed x plus c. And that is what the integral of cosine cubed x dx looks like. And that might have been surprising to us. I can understand why it would be, but that's the idea. And so the trick is, notice that the cosine cubed, I could take out 1 power of cosine and have an even power of cosine left, and I could do a substitution there, okay? All right, let's try another one and see if we can get a little better, or see if we can get a better trajectory of where we're trying to head with our strategy, okay? So here's example 2. This time I want to find the integral of sine to the 5th power cosine squared dx. Okay, so now that I have sine and cosine, maybe I could let, I don't know, u be cosine, but then I have sine to the 5th power, not just sine by itself, so I don't know if that's going to work. What could we do? Well, I think one thing we could do is, well, what did we do last time? We peeled out 1 cosine x, and then we recognized I could use a trig substitution to break down cosine squared in terms of sine squared. Maybe I could do something similar to that now. Alright, so what I'm going to do, notice I have an odd power of sine. So I'm going to take out 1 sine, so I have sine to the 4th x, cosine squared x, sine x, dx. Alright, I like this idea because I can write sine to the 4th as sine squared quantity squared. Okay, now why is that helpful? Because now remember, sine squared, I can use Pythagorean identity to rewrite it as cosine squared. And once I do that, I'm going to have a function of cosine times sine x dx. That's my U substitution. U is going to be cosine, dx is going to be, well, my du would be negative sine x dx, which I can get here. Okay, so I'm going to rewrite sine squared then as 1 minus cosine squared x squared, right, because it was the 4th power. And then I have cosine squared x sine x dx. And now I'm going to let's let u be what? Cosine x. Then du is negative sine x dx, which is almost what I have. I have negative du, right, because we don't have the negative 1 in there. So now my integral becomes negative 1 minus u squared times u squared du. And that is a polynomial, right? So I can factor that out. And when you do, let's see, you get, so you use the FOIL method on the 1 minus u squared. So you get 1 minus 1, or 1 times 1, and then negative 2u squared plus u to the 4th, all times u squared du. So then you end up with negative u squared minus 2u to the 4th plus u to the 6th, right? You have to add your exponents as you're distributing that u squared du. And so now I can integrate that and get negative, let's see, the integral of u squared, 1/3 u cubed. The integral of 2u to the 4th, you raise the power, divide by that power, right? So we get 2/5 u to the 5th power. And then u to the 6th, raised by the power, divide by that power, you get 1/7 u to the 7th power. Okay, all that plus c. And so finally I can go back and put in my sines and cosines. Or what was u? I can't remember now. U was cosine. Alright, so we have negative 1/3 cosine cubed x. I'm distributing my negative now. Plus 2/5 cosine of the 5th x, cosine of the 5th x minus 1/7 cosine of the 7th x plus c. And there is my integral. It's pretty wild. So when we have these sine cosines to powers, it looks like, at least for the first two examples, our answers come out to be some sort of polynomial in terms of either sine or cosine. Okay? Alright, now I wonder if this strategy works all the time. Well, not all the time, but most of the time. So, or maybe not even most of the time, but about half the time. Okay, so look, example 1 and 2, what did we have? We had cosine cubed. We had sine to the 5th x cosine squared. So both times we had a trig function to an odd power. If you have an odd power, you can always pull out one of those and then use a U substitution on the odd power. I mean on the even power. Courtney, why is the second u squared if sine isn't squared? Let's see. Are you talking about example 1 or example 2? Oh, let me see. Did I make a mistake here? Oh, okay. I think you may be talking about here. And so what that is talking about is, look, u is cosine. And so I had, there's one u squared, there's another u squared. So there's my u squared, and this is my du. Okay, I hope that answers your question. Let me know if you still have it, okay? All right, so let's look at an example where we don't have an odd power. So here's example 3, and I want to integrate 0 to pi sine squared x dx. All right, now this time I can't use the Pythagorean identity because it's not going to help me get a sine and a cosine, right? So actually getting a sine and a cosine in there helps us, right? Because it allows us to do U substitution. But with this, I can't do it. So what are we going to do? We have to use our half angle identities. And it's okay if you forgot those. Most people do. We don't use them every day, okay? But here is, well, this is a version of half angle identities solved for what we want, okay? So sine squared x is the same thing as 1/2 1 minus cosine 2x. And actually the trig book I'm teaching out of right now calls these reduction formulas because it takes sine squared and reduces the power down to 1, right, as cosine of the first power. You can do the same thing with cosine squared equals 1/2 1 plus cosine 2x. Okay, and we get these from the half angle identities. That's why I wrote that. So in trig, you learn that the half, let's see, cosine of 1/2 x equals the square root, it could be plus or minus depending on where you are, 1 plus cosine x over 2. All right, so what we're doing here, cosine squared x over 2. So what we're doing here is rearranging this to solve for that, okay? No, cosine, sorry. Actually, all we did was square both sides, right? You square both sides of this equation, and you get to what we have here, okay? And so that's where we're getting this, but don't worry too much about it. We're not really going to focus a lot on that, other than we're going to apply that to rewrite sine squared into something we can integrate. Okay, so here's what we're going to do. We're going to have 0 to pi. Instead of saying sine squared, which I can't integrate right now, I'm going to use this half angle identity, 1/2 1 minus cosine 2x dx. Right? I mean, isn't that what sine squared is? And so now that is something I can integrate with a U substitution. So I'm going to take out 1/2 0 to pi 1 minus cosine 2x dx. Okay, and so it'd probably be easiest to break it up. So the integral of the integral of 1 is x, which is pretty easy, and then we have minus 1/2 the integral 0 to pi cosine 2x dx, which we can easily integrate as well by letting u be 2x, and so du is 2 dx. And I like going through the details on this because it's easy to try to do mental math and jump ahead and make a mistake. So we get 1/2 du is dx here. So we end up with, let's see, the integral of cosine u du times 1/2. So we end up with 1/4. And then to figure out what my u should be, we can just say, look, if x is 0, that means u is also 0. Okay, and if x is pi, then u is 2 pi. So now I'm just going from 0 to 2 pi, and I had 1/2 x 0 to pi. Okay, so we know the 1/2 x 0 to pi is going to be what? 1/2 times pi over 2. And then the integral of cosine u is what? Sine u. So we have 1/4 sine u going from 0 to 2 pi. But notice, so we end up with pi over 2 minus 1/4 times sine of 2 pi minus sine of 0. But sine of 0 and sine of 2 pi are the same thing, right? So this all ends up being just the value pi over 2. Okay, I hope that makes sense. The definite integral part is something we've seen before. I want you to know how to do that, but that's not really why we bring out this example. The reason we bring out this example is we want to be able to identify this substitution. So I'm using sine squared. I'm using the half angle identity to sub out sine squared to something I can actually use. Okay, and we can do the same thing in the next example, example 4. If that doesn't make sense, please let me know. Okay, I want to help. I want to make sure you do, that you feel good about it. So if I have the integral of sine to the 4th power of x, it's kind of the same deal, right? I mean, I don't have an odd power, so I can't take out a cosine. I mean, if you tried, or take out a sine, if you try to do that, if you had sine cubed x, sine x dx, I can't use Pythagorean identity to sub out sine cubed, all right? So Pythagorean identity doesn't help. So that's when we have only even powers, we're going to have to use this half angle identity idea. Okay, so what we're going to do here is I'm going to rewrite this as sine squared squared. And now I can use my half angle identity, and I'll end up with, what do we say? 1/2 1 minus cosine 2x, all that quantity squared. Okay, so you have 1/2 1 minus cosine 2x quantity squared dx, like that. Okay, now I can FOIL that out. So let's see, the 1/2 squared is a 1/4. Let's go ahead and take that out. So I have 1/4, and then FOILing out 1 minus cosine 2x, I end up with 1 minus 2 copies of cosine 2x plus cosine squared of 2x dx. Okay, and so now I got to integrate this thing. Well, we have another cosine squared, so what can we possibly do? So on this cosine squared here, I'm actually going to use the half angle identity again, or my reduction formula again. All right, so here I end up with, let's see if this makes sense. I'm going to have 1/4. Well, let's go ahead and integrate the 1 and the 2 cosine 2x. Okay, so, and well, I'm backtracking even more. Let's just leave it like it is for the moment. Let's get our reduction formula in, and then we'll clean it up. Okay, so the cosine squared 2x, right, again, we're going to use this identity that cosine squared x is 1/2 1 plus cosine 2x, but this time we're replacing x with 2x. So it's going to go 1/2 1 plus cosine 4x. Right, you have to double that angle, and we have dx of all this. All right, so this is what we end up with, okay? And so just simplifying, let's see, we end up with well, let's see, we have the 1 and the 1/2, right? That's going to be 3/2. And then we have minus 2 cosine 2x plus 1/2 cosine 4x. At this point, we just need to make sure we do our U substitutions correctly. So we're going to have two of them. We're going to first let u be 2x. So then du is 2 dx, which actually we have here. Okay, so that's good. We don't have to even compensate anything. Here on this side, we're going to have u be 4x. So du is 4 dx. We don't have that. We have 1/4 of that. All right, so here to compensate my constants, let's see, we're going to have 1/4. The integral of 3/2 is just 3/2 x. Not a big deal. The integral now of, so let me say minus the integral of what? Well, the 2x is there. The 2 dx is right here. So I just integrate cosine u du. Not a big deal. Plus, on this side, I only had, let's see, we had the integral of cosine u, but then we needed to multiply in a fourth, so I have 1/8 integral of cosine u du. I hope that makes sense for us. All right, and remember, all this is being multiplied by 1/4. I haven't even put that in. Okay, so here, let's see, we get 1/4 times 3/2 x minus the integral of cosine u, which is sine u. And I'm going to go ahead and replace that with sine 2x. And then the integral of cosine u, and you know what would have been smarter for me to do? Instead of using u twice, maybe instead of a u substitution, we do a w substitution. So w equals 4x. So then here I have dw is 4dx, and then we have 1/4 dw equals dx. So now I'm integrating cosine w dw, and that's just so I don't confuse myself in my work. The integral of cosine w is sine w, so I have 1/8 sine, what was w? 4x. Okay, and then all that plus c, and I have my 1/4 distributing across there. And I mean, I could distribute the 1/4, but we get the idea. We've already done the hard part. So there's my integral right there. I hope that makes sense. Now, this one may have looked a little bit more complicated. Why? Because I had to do the reduction formula there to get here, but then I had to do the reduction formula again to get here. So actually I had to do the reduction formula twice when I had sine to the 4th power. Okay, and then we had 2 different u substitutions, and then if we're careful with our work, I think we can follow it, make sure it looks good. Okay, if you have any questions on this though, please let me know. This is a little bit different, but we're just applying trig identities to reduce it down, okay? And I think now we're able to summarize what we've done so far with a table. So let's see. What we want to do is integrate. So to integrate, let me say it like this. Integrating sine to the mx power cosine to the nx power dx. All right, so sine mx times cosine nx. All right, now we have options here. If either m or n is odd, we can pull out one of those trig values and do a u substitution directly. Okay, so I'm just going to follow the way the book writes this, but really we could say if either m or n is odd. Okay, so if n is odd, and for those of you who've had discrete math, remember we define an odd number as 2 times some number plus 1. Then you can use, so this time cosine is to an odd power. We're going to take out a cosine. We can use that cosine squared x equals 1 minus sine squared x, and let u be the sine x and du be your cosine x dx. Okay, so it'll look something like this. You have the integral of sine to the m, cosine to the n. Now remember, let's replace cosine to the n with that odd power we said it was 2k plus 1. And so what I can do here is I can say sine of the mx cosine to the 2k power times cosine x dx. And now I can replace the cosine squared, because remember cosine squared is the same thing as saying cosine squared to the k power, right? That's the same thing. So I can take the cosine squared in the middle of sine m to x. Cosine squared is the same as 1 minus sine squared to the k power cosine x dx. And there's where I have my u substitution. Okay, does that make sense? Now, let's suppose n is even. Okay, so if n is even, but your m is odd, then we can do the same thing, except instead of replacing cosine, we can replace sine, and we can use our U substitution to be cosine x. Okay, so if m is odd, and here again that means 2k plus 1 for m, we're just going to follow the previous statement. Then we can use that sine squared of x is 1 minus cosine squared, and we let u be, this time, cosine x, and du, the only thing we have to worry about is the derivative of cosine x is negative, right? So we have negative sine x dx, like that. All right, so other than that, though, it follows the same pattern. We're going to, I guess I can write it up, why not? We have sine to the mx, cosine to the nx dx, and this time sine is what equals 2k plus 1. So that's the same thing then as the integral of sine squared x to the k power cosine x times sine x dx. And so from there, I can say that I'll replace sine squared using my Pythagorean identity. That's going to be 1 minus cosine squared to the k power cosine nx times sine x dx, and now I can use my U substitution like I want. Make sense? Okay. So that is the case. Let's see, we have n is odd. If n is odd, we've got it. If m is odd, we've got it. What if neither are odd? Okay, so that's the third case. If m and n are both even, we're going to have to use a reduction formula. Okay, so we use half angle identities. And again, let's see, identities. Yeah, got my spelling mixed up, sorry. And that's going to be cosine squared, let's say x is 1/2 1 plus cosine 2x, and sine squared x is 1/2 1 minus cosine 2x. Okay, so we'll use one of those to reduce. Okay, and the book also points out sometimes, so every once in a while, it may be useful. Let's say this may be helpful. And we're getting this idea from the double angle identity for sine 2x equals 2 cosine x sine x. Okay, that may be helpful every once in a while. If you just, like if we're trying to integrate cosine x sine x, well, you could use a U substitution, I guess, or you could say that's 1/2 sine 2x, and then use the U substitution. Okay, so every once in a while that may be a helpful tool to have. All right, now, so this is everything we've done so far is sine and cosine. What about other stuff? What else could you do? Well, so let me show you the strategy still works for tangent and secant, and the only thing is, well, let's just look at it. Okay, so this is example 5 in your textbook, and we have tangent to the 6th power of x, secant to the 4th power of x dx. All right, so now look, if we were using the flowchart we just came up with, well, they're both even, right? We have both even, so would we have to do a reduction formula? Well, maybe not, because tangent and secant work a little bit differently. Remember, the derivative of secant is actually secant squared. Okay, so from here, I could replace, here's what I'm going to do. I'm going to say, we have the integral of tangent to the 6th power of x. And then instead of saying secant to the 4th power, I'm going to take out not just one secant, I'm going to take out secant squared. We have secant squared x times secant squared x dx. Now, this I recognize as du. Du is secant squared x dx. If du is secant squared dx, what would u be? U is going to be tangent x, right? The derivative of tangent is secant squared, okay? And so can I rewrite secant squared in terms of tangent? Now, way back at the beginning, I said, look, remember the Pythagorean identities, that this is going to be the same thing as saying tangent to the 6x power, and I can rewrite secant squared as 1 plus tangent x. 1 plus tangent squared x. And now I can do a U substitution. We let u be tangent, du be secant squared, and so I end up with u to the 6th power times 1 plus u squared. And then what about secant squared x dx? That's my U substitution, right? That's dx there, or du, I mean. So I just get du. So this whole thing turned into just this pretty simple polynomial, which is pretty incredible. So I'm just trying to integrate now u to the 6th plus u to the 8th du. And that's kind of like a day one integral, right? Let's see. So that's going to be 1/7 u to the 7th plus 1/9, u to the 9th plus c. And so as our answer then, let's go back, what was u? Tangent. My integral becomes 1/7 tangent to the 7th power x plus 1/9 tangent to the 9th power x plus c. And there it is. And it's funny, I mean, before today you probably never thought of like tangent to the 9th power, like that even being useful. But here we have it. So when we're integrating these powers of tangent and secant, it's similar to what we did with sine and cosine, but if you have secant to an even power instead of an odd power like we did with sine and cosine, if you have secant to an even power, you can take out secant squared, and now you can use your Pythagorean identity to reduce secant into terms of tangent. Okay? Great. Let's look at some more examples of this. Okay, so let's see, I need to come up at the top. We've had a lot of notes. These integrals take up room, don't they? Okay, so let's look at example 6. And this time we want to integrate tangent to the 5th power, secant to the, please be even, it's not, secant to the 7th power. Alright, so this time tangent is odd, secant is odd. I can't take out secant squared. What can I possibly do? Okay, so let's think. Well, what's the derivative of secant? The derivative of secant is secant times tangent. Oh, okay, I got an idea. Let's do this. Let's take out this time, let's take out a tangent and a secant. So here I have to the side secant theta, or let's say, sorry, tangent theta, secant theta, d theta. Now the reason I did that is because I can recognize that this secant tangent over here at the end is going to be my du. Du is secant theta, tan theta. And what kind of function would that come from? Well, the derivative of secant, remember, is secant tangent. Okay, so I'm going to let u be secant, which means I need to replace my tangents in terms of secants. I can do that though, right? Because this is the same thing as saying tangent squared theta quantity squared times tangent theta secant theta d theta over here. Okay, and remember the Pythagorean identity, I can rewrite tangent squared as what? Secant squared minus 1. Okay, so here I have the integral of, this is secant squared minus 1 squared, and then I have secant squared, or secant to the 6th power times my tangent secant, and now I can apply my U substitution. Okay, so the U substitution, again, U is going to be secant, so there's my U, and that's my du. Okay, so I end up now with, what is that? U squared minus 1 quantity squared times u to the 6th du. And that's just a simple polynomial. Okay, that's a simple polynomial. All right, so you FOIL this out. You should get, after you distribute and everything, u to the 10th minus 2u to the 8th power plus u to the 6th du. And so we can integrate now and get 1/11. Let's go ahead and replace our u. What was our u? Secant. So we have 1/11 u to the 11th. So that's 1/11 secant to the 11th power minus, let's see, 2/9 secant to the 9th power plus u to the 6th. The integral of that would be 1/7 u to the 7th. So that's 1/7 secant to the 7th power plus c. And there is our integral. Make sense? Okay, so I think with these two cases, we kind of get a good idea of how to integrate our secant tangents. So let's see. So here's our strategy. So integrating something like this. The integral of tangent to the m, secant to the n, dx. All right, so if, let's say 1. If n, last time it was odd, right? If n was odd, if m is odd, here we're going to say if n is even, so if you have even secant, then we're going to let u be, right, the u is going to be tangent, and du is going to be secant squared. Okay, and so the idea is, here you have the integral of tangent to the m, secant to the n, and remember n is the same thing as 2k, right, because that's how you define an even number, right? Even would be a multiple of 2. And so what I can do then is take out secant squared. So I have something like this, tangent to the mx. Let's see, we're going to take out a secant squared dx. If I did that, what am I left with? I'm left with a secant to the 2k minus 2 power. Or another way of saying that is secant squared to the k minus 1 power. All right, and so from there, I can rewrite this as tangent to the m power. The secant squared is, what, 1 plus tangent squared to the k minus 1 power times secant squared dx. And now I can use my U substitution. You see, there's my du, and that's my u. Okay, so if n is even, that's what we do. Now, if it's not, if n is odd, then hopefully m is even. I mean, if m is odd as well. Okay, and so that means 2k plus 1. And if that's the case, what are we going to do? We're going to let u be secant, because what we're peeling out now is a secant tangent. All right, and so the idea is like this. We have, again, we have tangent mx secant to the nx dx. Here my m is what? My m is odd, so I have 2k plus 1. And in this case, think about it. If part 1 failed, then here n is also 2k plus 1 for a different k. So let's say 2k1 plus 1 and 2k2 plus 1. Then what I can do here is peel out. I'm going to peel out a secant x tangent x dx. And that's going to be my my du, sorry. So what did I take out from everything else? I took out one tangent, so I have tangent to the 2k. So I'm going to say it like this, tangent squared to the k1 power. And then same with secant, secant squared to the k2 power. And now I can rewrite, I'm letting du is secant tangent x, right? So my U substitution is going to be secant. So I need to replace tangent squared with the Pythagorean identity secant squared x minus 1 to the k1 times secant squared x to the k2 times my du secant x tangent x dx. All right, and so there's my u and there's my du. I hope that makes sense. All right, sometimes looking at the general formulas are confusing, but hopefully with examples 5 and 6, it makes sense to us. All right, now let's see. So we covered the case if n is even, and then we cover the case where n is odd and m is odd. What happens if n is odd and the tangent is even? Well, that could be difficult and that's actually a case we don't really consider here. Okay. All right. Now, here's a couple of things that will be useful. So we're kind of picking up some tidbits. If you remember, let's make this last section called let's just call it other things. Other things to consider. All right, so if you remember the integral of tangent x dx, do you remember how to do that? We actually got ln secant x plus c. And how did we get that? The way we got that was we said tangent x is the same thing as sine over cosine. And so once we do a U substitution, we get negative 1 over u du. And so we end up with negative ln cosine x plus c. But remember, the negative for a logarithm can be pulled in as a power, so we end up with ln the reciprocal of cosine plus c. That's how we get that. Okay, that's how we did it. All right, so this is also going to allow us, a strategy similar to that is going to allow us now to integrate secant x dx. Okay, just integral secant. We haven't calculated that before. And it's going to be something, if you saw this in a table of integrals, you probably wondered how on earth did they get that. So I'm going to show you, and it's kind of surprising, but this is a really neat trick. I like this a lot. So here we have the integral of secant x, and I'm going to multiply something in the numerator and the denominator. And I think it's going to be obvious to us. It's going to be secant x plus tangent x divided by secant x plus tangent x. Doesn't that seem obvious to you? Probably not. I'm being a little sarcastic, but watch what happens. So in the numerator, I distribute the secant x. I get secant x squared, or secant squared x, sorry, plus secant x tan x over secant x plus tangent x. Now, don't these two expressions look familiar? Secant squared is the derivative of tangent, and secant tangent is the derivative of secant. So what I'm going to do here is I'm going to let u be this secant x plus tan x. And when I do that, what's its derivative? What's du? The derivative of secant is secant tangent. The derivative of tangent is secant squared dx. So now look what my integral becomes. This is amazing. It becomes the integral of 1 over u du. Right? The secant plus tangent is my u. Secant squared plus secant tangent is my du. So I get 1 over u du, which means the integral of that we know is ln absolute value of u plus c. So the integral of secant x, let's rewrite it then. The integral of secant x dx is ln absolute value of secant x plus tangent x plus c. And there it is. There's the integral of secant. And how did they get that? Through this very clever technique of multiplying in secant x plus tangent x over secant x plus tangent x. And that's a really cool thing. That'd be a cool trick to keep in mind. All right. So what this will allow us to do then is worry about the cases between these two things. What happens if we have an odd power? So for example, what I mean is, like, if I'm integrating something like this, tangent cubed x dx, how on earth can I do that? All right, so I'm going to first peel out a tangent squared. So I'm going to have tangent, I'm actually going to write it like this, tangent x times tangent squared x dx. And then I can use a substitution on tangent squared. So I get the even power, so I can put in a secant. All right, so tangent squared is the same as secant squared x minus 1 dx from my Pythagorean identity. Okay, and now what I'm going to do is distribute the tangent and break this up as two different integrals. So I'm going to have the integral of secant squared x tangent x. I don't know why I wrote it that way. Let's write it as tangent x secant squared x minus the integral of tangent x dx. All right? Okay, now what is the integral of tangent x Can you even read that? It says tangent x. Let me try this again. Sorry, my handwriting's so bad. If you let u be tan x, du is what? Secant squared x dx. This is going to be the integral of u squared. All right, or I'm sorry, the integral of u. Sorry, so the integral of u, we get 1/2 u squared, so get 1/2 tangent squared. And then the integral of tangent, well, we know that to be ln secant x dx. So there we have it, 1/2 tangent squared minus ln secant x dx. That's our answer. Not dx, I'm sorry. I meant to say, when you integrate, what do you say? Plus c, right? That's what I was thinking in my head, but I was writing and saying the wrong thing. All right, so plus c. Makes sense? Makes sense? Yeah? Hope so. All right, let's look at a couple more. I have a couple more examples I want to show you. So let's take example 8. This time we're going to integrate secant cubed dx. Secant cubed. So what can you do with secant cubed? We're actually going to have to implement something we learned last time, integration by parts, which makes me excited because I want to make sure that you get this. Okay, so we're going to have a u and a dv, right? We got to figure out u and dv. And here's the trick. I mean, what could possibly be the dv? Well, I mean, I guess we could try to integrate secant, but I think it makes more sense to let dv be secant squared x dx. And if that's the case, that only leaves u to be secant. So then du is the derivative secant, and in the integral of secant squared x dx is tangent x. All right, so then remember integration by parts. Let me write it up real quick. I think it's good to see. The integration by parts says that the integral of u times dv equals uv minus the integral of v du. Do you remember how we got that? Through product rule, right? This is the integration version of product rule. And so now if I plug in what we just had to get this integral, we have the integral of u dv, which is secant cubed x dx, is uv. So it's going to be, let's put equals uv secant x tangent x minus the integral of v, which is tangent x, times du, which is secant x. Okay, the integral of tangent x secant x, well, that's secant x, right? The derivative of secant x is tan x secant x. Here we have dx, right? So here we end up with secant x tangent x minus the integral of tan secant, which is secant x plus c. And there is my integral for secant cubed using integration by parts. Okay, so when we have just odd powers, there's not exactly just a flat formula, but using these integrals of tangent x and secant x, understanding integration by parts, we kind of pick at the pieces like that, right? All right, so let me show you one more. Okay, so there's one more kind of funny type of integral. What if I did something like this? So this is example 9. I want to integrate this time sine to the 4th x cosine to the 5th x dx. All right, so I'm going to integrate sine. That's not sine to the 4th. That's what I said, but that's not what I mean. Sine of 4x and cosine of 5x. So we have different angles, sine and cosine with two different angles. All right, what can we do? We are going to go deep into the lexicon of trigonometric identities to use our product to sum identities. It's okay if you don't know these. In fact, when I teach trigonometry, I tell them you're never going to need these, or you're going to need these only like a handful of times. And that's true from my experience, at least. I've only had to use them a handful of times, and usually I can reference them. All right, so here's what we're going to use. This is product Alright, I think I'm back. Sorry. I had a, I got booted off the internet real quick. Okay, so let's just finish this example real quick. And we're going to use something, is this the product sum identity we're going to use? Yes. So I'm not going to write the others down, but you can find them in the book. So find others in, really in any trig text. Okay, and you can just reference those as you need. All right, now to integrate this then, we recognize that this is A and this is B. So I'm going to say that this is the integral of, according to my product here, or my identity, 1/2, let's see, sine of A minus B. A was what? 4x, and B was 5x. So A minus is going to be minus x plus sine of A plus B, which would be 9x dx. Okay, and now I can use substitutions on both of those to integrate. And so you end up with, if you just do your U substitutions and integrate carefully, you end up with 1/2 cosine x minus 1/9 sine x, cosine 9x plus c. All right, and that's 1/2. I didn't distribute the 1/2 there. All right, so I hope that makes sense. All right, so we made it mostly through class without any internet glitches, but here we are. Finally, we're done. If you have any questions on this, please let me know. I'd be glad to help. This is 7.2. We'll pick up with 7.3 next week. If you have any questions, again, I want to help you. Just let me know. Communicate, okay? Hope you guys are doing well. Hope you guys have a great weekend. We'll see you on Tuesday. Take care, guys.